This is problem 52. It's on page 305. There's no description. It's just a beam with two simple supports. There's a cantilever on the right-hand side and two individual loads as well as a distributed load. I'll sketch the beam up here so that I can create shear and moment diagrams beneath it. There's a reaction on the left end and a reaction near the right. There's a distributed load along the entire length of the beam, and that distributed load has magnitude of 4 kips per foot. Then there's a concentrated load of 15 kips. That is 8 feet from the left-hand side. There's another 8 foot to the support. And then there's 4 feet beyond the support with a 12 kip load out at the end. Let's see, so let's call this A, let's call this B. The first step is to solve for the reactions A and B. So we'll just use statics to do that. Summing moments about A on this side, we'd have 16 feet multiplied by B. That'll take care of the reaction at B, so summing moments counterclockwise positive. Let's see, so that takes care of B. Then we've got all the applied loads. Minus 8 feet times 15K minus 20 feet multiplied by the load there, which is 12K. And then the distributed load, its center acts 10 feet from A, okay, because it's just 8 and 8 is 16 and 4 is 20. So the resultant acts at 10 feet, and the 4K per foot acts over a distance of 20 feet. Okay, that moment all comes up to 0. When you solve for B, the reaction at B, let's go ahead and write it down here. What you get is 72.5 kips. Summing moments, again counterclockwise positive about B. What you get is negative 16 feet multiplied by A. Understand that A is causing a negative moment about B. Summing moments about this point. Okay. Plus 6 feet multiplied by 4K per foot times 20 feet to take care of the distributed load. Now understand that the center of the distributed load is in the center of the beam, and that's only 6 feet from the support B. Okay, so that takes care of the reaction, the distributed load. Then we also have the 8-foot position of the 15 kip load. So that's right here, it's 8 feet away from B, and it of course causes a positive moment. Then finally, the 12 kip load acts 4 feet from B, and of course causes a negative moment. So solving for the reaction at A, which is the only unknown in the second moment equation, you'll find that it's 34.5 kips. Now if you add 34.5 to 72.5, you'll find that balances the load. So summing forces in the y direction, you find it is in fact 0 with these reactions. So we're certain that we have a correct solution here. Now, the next part is to come up with the shear and moment diagrams. So that'll be enough for the shear. Our position is measured in feet along the beam. And so if you imagine just a section of the beam on the left-hand side, well then the shear is going to begin at a load of 34, I'll make this match, 34.5 kips. And as this distributed load is applied along the length of the beam, the amount of shear force required to resist this reaction becomes less and less because the distributed load is helping. So basically, the shear is going to decrease at a rate of 4 kips per foot. So each foot, there's 4 more kips taken away from 34.5. Now, 8 times 4 gives you 32. So if you take 32 from 34.5, what you find is that you end up at 2.5 kips. So the amount of shear, the amount of downward shear required just before this 15 kip load is only 2.5 kips. Of course, that 15 kip load reverses the shear. Now the shear has to be up to hold the beam in equilibrium. How far does it move? Well, it moves down by 15. So 2.5 minus 15 will bring us down to, let's try to keep a decent scale here, negative 12.5 kips. So now the shear is up. Okay. Now the distributed load keeps adding more load to the beam, so that now the shear has to be larger, but it's still negative. So it's going to, again, move down at the same slope as before, 4 kips per foot. But it'll finally come to this reaction here, and that's another 8 feet. So we have to subtract off 8 feet worth of 4 kips per foot, which is 32 kips total. So subtracting 32 from 12.5 will end up with a shear load of negative 44.5 kips. It's supposed to be a straight line. Okay? Now at this point, the reaction load at B, 72.5 kips, acts upward and moves us up above the line. So if you take 72.5, subtract 44.5, that's how far up you can go, because that would be the shear now acting downward. Doing the math, it comes out to 28 kips. And then again, we've got 4 kips per foot, multiplied by 4 feet is 16 kips. It'll come down. 16 from 12 leaves you with, or excuse me, 16 from 28 leaves you with 12. And so same slope down to 12 kips, where finally the load at the end pulls us back down to the axis. So the shear to the right of this is 0. Okay, so there's our shear diagram. What about the moment diagram? Again, position in feet and moment in foot kips. Okay. So to the left of the beam, there's no moment because there's no beam. So we have to begin at 0. And notice that we're adding area very quickly at the beginning, but slower later on. So that we expect somewhat of a concave down type of shape. So something like this. Notice also that at this point, the shear is discontinuous. That means that the slope goes from a positive 2.5 suddenly to a negative 12.5. So there's a discontinuity here. It's not a smooth curve. And what is the value of this point? Well, it's just this area. So if you take 34.5 plus 2.5, of course you get, what, 37? Okay, 37 divided by 2 to get the average height multiplied by 8 turns out to be 148. So the magnitude of the moment in the beam at this point, which is just beneath this 15 kip load, is 148 foot kips or kip feet. Okay, and I'll make a note that this is discontinuous. Probably going to run out of room if I don't break the word. Okay, so then what about this area? Well, this area is actually larger because notice that the distance is the same, but the magnitude of the heights are much larger. And so I don't remember exactly what I got for this area. You can calculate it, but basically just take 12.5 plus 44.5. Okay, divide that by 2 and multiply by 8. That'll give you the change in the moment. And it came out to a negative 80. Pretty far down here. A negative 80 foot kips. Okay? And then finally calculating this area, 28 and 12 are 40. So divided by 2 is 20. So the average height is 20 times 4, which is 80. Sure enough, it comes back to 0, so that's a good thing. Again, notice, before I draw that, notice that we're adding more area at the beginning, so expect a concave down shape. So it is appropriate to draw it that way. All right, so to be very clear, that point's right there. This point is here, and this one's right here. Okay? So there's the shear in the moment diagram, but that's not enough because we don't really know the shape of these curves. We know they're concave down, but beyond that, we couldn't say we couldn't compute the moment at any point. Okay, so how do we deal with that? Well, here's what I did. I said, I'm going to break the beam up into sections between 0 and 8 feet, between 8 and 16 feet, and then finally between 16 and 20 feet. Okay, so I'm looking at this section, and this section. So it's here, here, and here. Okay? And I just figured out the shear as a function of position in those sections. Notice it's just a straight line in all three sections. It has the same slope in all three sections. It's -4 kips per foot. Okay? And then all I had to do was figure out the intercept, essentially, in order to make everything work. Well, that came out to 34.5 for the first equation. For the next equation, I'll tell you what, let's do it this way. Let's make more of a table. So here's V of X. There we go. Okay, so the shear is a function of position. Well, again, the slope is the same in all of these sections, right? This slope of this line is the same because that's just due to the distributed load. It is the intercept that's different, and the intercepts I got were 19.5 for that section, and then 92 for this section. You can verify that these are correct. Just plug in different X positions, 0, 8 to 8 in this one, 8 to 16 in this one, 16 to 20 in this one, and you'll find that it matches what we've got here on the diagram. The next thing to do was to calculate the moment, and the moment's pretty straightforward. Made a table here. Let me go ahead and erase the table for the time being, and then we'll extend it later if we need it. I'll use this space down here to integrate. So let's work on this one first. The moment is the integral of the shear, and so this would be the integral of -4x plus 34.5 dx. When you do the math, -4x squared over 2 plus 34.5x plus some constant. Well, now we have to plug in the limits. We're working between here and here. So you can plug in x equals 0. That makes it very easy because at that point the moment's 0, and you find that this constant must be 0. So the moment as a function of x, the first one, is just going to be, notice I'll take -4 over 2 is -2, x squared plus 34.5x. Okay, so that takes care of the first one. Let's integrate the second one. Of course, the only change is the constant, right? So 19.5 dx. So we end up with 19.5x plus some constant. I'm integrating this section now. Now you can plug in either x equal 8 or x equals 16 because you know the value of the moment at either place. When you do that, you'll find out the value of the constant is 120. And again, you can plug in x between 8 and 16 into this equation. You'll see that it works. So -2x squared plus 19.5x plus 120. Now, understand this only works for the section from x equal 8 feet to x equal 16 feet. Okay? Do the same thing for the last section. The only thing that changes is the constant again, as well as the constant of integration. Plug in the limits either here or here. The easy one is over here, right? Because at x equal to 20, the moment should come out to 0. When you plug in the numbers, you find that c is a -1040. Okay, so the moment comes out to -2x squared plus 92x minus 1040. Okay, so there's the moments as a function of position. And of course, as you look at these, you can verify that they're correct by plugging in the various positions along the curve. And there's something else I wanted to tell you. Oh, yeah, these are, since the shear is all first order, these moment curves are all second order, which makes sense. You can see it right there. There's the first order in the shear, just x. You've got x squareds in the moment, which are second order, and they're all concave down.